Hello, everybody. In this video, we're going to dive into some additional integration techniques. So I know we've been going through a lot of them. The one we'll dive into today is called partial fraction decomposition. So we're not going to dive into everything, but we'll dive into probably the most important things for what this means exactly. But basically, the idea is that we have one expression and we break it down into multiple fractions that are then easier to integrate. And you'll see how we do this. So let me share my screen. If anybody has any questions, by the way, as usual, feel free to just drop them in the chat and then we can kind of talk about them there. So basically, the idea to start is that we start off with something that might be tough to integrate. So let me give an example. And by the way, when we're using this technique, we're dealing with rational functions. What is a rational function? You might think, rational just in like plain English means like logical or it makes sense. That's not what we mean here. Think of the word rational like ratio. Ratio. No. So we're talking about ratios, in other words. So specifically, we're talking about ratios of polynomials. So if we have like x squared plus 5x, I'll just make that up. And then we have x squared minus 25. This, in its current form, again, we've talked about u substitution, we've talked about integration by parts. Neither of those would really work here, right? Because if you tried u sub, the only choice of u would be the entire denominator. So you would need a 2x in the numerator. But the problem is like this is proportional, or you need something proportional to that. 5x would work, but the x squared plus part does not work. So that's a problem. Luckily here, though, what you can do is you can factor, right? So if you factor this, think about it, we can factor out an x from here and get x times x plus 5, right? And then we could, down here, do x minus 5 times x plus 5. And there we can just algebraically simplify that. And once we do that, those cancel out. Again, this is actually now solvable with u sub, I'll say. It is a little bit more advanced, but it's a little bit more advanced of a u sub technique. There's like an additional step you need beyond what we're used to, but this is now solvable. If this changed in any way, so if this like changed, then it might not be solvable. So if this was like 24, for example, then it would not be solvable. And that's kind of what we want to deal with today. We want to deal with problems like this, not necessarily this exact problem, but this type of problem where it's not in a form already where either u sub works, that would be a viable strategy, or where just we can simplify algebraically. We're assuming that both of those break down. So what are some examples? Let me actually grab some examples. Yeah, it'd be better for me to grab some rather than make up my own, because they'll be better examples. So here, let me grab one. So yeah, I think this is a good one to try first. So yeah, let's just do this, because this is like the simplest case. So I'll pop this in and then we'll go through this. So if we're looking at this, we're looking to integrate this first. So again, this is technically a rational function. And you might think, wait a second, I thought a rational function was a polynomial divided by another polynomial. It is. 4 itself is a polynomial technically. So 4 counts as a polynomial. So that's still technically true. Like it's a 0th degree polynomial. And if that doesn't make sense, by the way, think of it like this. If I have like 3x squared plus 4x plus 4x minus 5, that's a 2nd degree polynomial, right? And then if I get rid of the first one, if I cross that out, I would just be left with 4x minus 5. That's a 1st degree polynomial because it has x to the first power. If I do that same pattern again, that, just the number, -5 or plus 5 or anything, is a 0th degree polynomial. Because the way you can kind of look at it is pretend like there's an x to the 0 here. X to the 0 is 1. So the constant term, it's like, x to the 2nd, x to the 1st, x to the 0th. So that's the sense in which just numbers themselves count as basically arbitrary, or not arbitrary constants, set like 0th degree polynomials. So it fits the same pattern, basically. But anyway, first, I think it's probably easiest to just kind of introduce the rules. So we won't dive into the why in as much detail behind the rules. I think it's easiest actually if we just start using it. So here are the rules that have been developed to always work with partial fractions. Rule number 0. If the degree of the, and you'll see why I say 0, because normally you don't have to do this rule. It only comes up sometimes, but you technically do need to check it. If the degree of the numerator is greater than, actually, is greater than or equal to the degree of the denominator, start with long division. Start with polynomial long division, which is a separate technique, arguably. There are some integrals that can be solved just with polynomial long division. You don't even do the partial fraction decomposition. But anyway, that process, I guess, how should I word it? That process of polynomial long division is basically, or I guess, how should I word it? It's basically a way, like in the context of this problem, it's a way to force the degree of the numerator to be less than. So that's really what we want. If the degree of the numerator, which it is here, right, 0, 2, the degree of the numerator is less than the degree of the denominator. If it's not, if it's greater than or equal to, so you got to watch greater than as well. So like if it was x squared here, we would have to start this problem, or we would have to start this problem with polynomial long division. It has to be less than, not greater than is not good enough. So that happens sometimes. Like I said, this maybe only happens like 10 to 15% of the time. Most of the time you don't have it, which is kind of why I label it rule 0. Usually you don't have to do it. For the second rule, or for rule number 1, if you will, basically factor the denominator. So factor the denominator. In order for polynomial long division to work, you have to be able to factor the denominator. Kind of, you don't always have to completely factor it, but you have to be able to factor it to some degree, in order to simplify it. Next, here's the interesting part. Basically, the factors in denominator on left become denominators in terms on the right. That's that. And then for number 3 here, so for number 3, what do we do here? Basically, this again, 3 usually doesn't come up. Like usually you just have to do rules 1, 2, and 4. I'm just giving the full process that will always work, even though some of the steps might not work every time. Step 3 is basically repeated roots, or basically repeated roots on the left, like have to have multiple denominators on right, counting up from 1 to the power. That might not make complete sense. That again, you don't have to worry about it. You'll see how this process works once we actually do it. And then step 4 is basically the numerator of each term on the right. So this is not how to solve the entire problem. This is just how to set it up correctly. So how to set up partial fraction decomposition. So how to set up partial fraction decomposition. The numerator of each term on the right is a polynomial that is 1 degree less than the denominator. Again, these rules seem really specific and really arbitrary, but you'll see how we actually apply them. But those are the rules. And if you get these rules, like I said, you'll see how we apply them. So here, let's just do rule 0. So when we do rule 0, here, what's rule 0? If the degree of the numerator is greater than or equal to the degree of the denominator, start with polynomial long division. Here, it's not. So we just don't do anything. Rule number 1, factor the denominator on the left, which is all we have here. And by the way, this is just to point out, this is not a calculus technique. Let me be 100% clear. Partial fraction decomposition is an algebra technique, purely. It has nothing to do with calculus. The reason we care about it in calculus is because, just practically speaking, after you do the decomposition, it's a lot easier to integrate. So that's why we use it as an integration technique, but it's not really a calculus technique. It's really just a pure algebra technique. It's just very useful here. So there you go. How would we factor the denominator here? Well, which 2 numbers would add up to negative 14 add up to 5 and multiply to negative 14? If you think about it for a while, and this is where having your factoring skills can be helpful. But actually, it'd be x plus 7 and then x minus 2, right? 7 times negative 2 is negative 14. Check. 7 minus 2 is 5, positive 5. So that works. Cool. So there you go. That's step 1. Now, how do we do step 2? The factors in the denominator on the left become denominators in terms on the right. Remember, what's a term? A term is like something plus something else. Like these would each be terms. So basically, for every factor, so here's one factor on the left, that would become a denominator in a term on the right. And I'm going to leave the numerator. I won't do anything with the numerator. And then here for this one, x minus 2, we'll do the same thing. X minus 2, like that. So there you go. Hopefully that makes sense. So basically, each factor in the denominator on the left, like I said, becomes a denominator in its own term on the right. That's what we're seeing here. So that's good. That's rule number 2. So we've done that. Now rule number 3 here, we don't have to do. So rule number 3 is just, nothing. So nothing to do there because we don't have repeated roots. What would a repeated root mean? It would mean, again, what do we mean by roots? We mean factors. Factors, roots, x-intercept, they all mean the same thing. We would basically mean they are repeated, as in we have multiple of the same one. So here, if you have like x plus 7 times x minus 2 times x minus 2, you have 2 of these. The root 2 is repeated. And you can combine that, by the way, by just having a number here, right? X minus 2, the whole thing squared. This has, again, to dive into the algebra terminology, this is called a multiplicity. So that's the official word, multiplicity. But you could have a multiplicity, and if you did, that's what it would be. So you have to watch that, but that's kind of the idea. And then now, here we don't, by the way. Here, right? Everything's just 1. So you don't have to deal with repeated roots. You only have to deal with them if there was if there was a repeated root, if there was a 2 here or a 3 here, for example, then you'd have to do rule number 3. So that's why I say like rule number 0 and rule number 3, you usually don't have to do. It's just to check to check everything you need and make sure you're not missing anything. I'm including them for that reason. So that's good. And then now let's see this. So step 4 is the numerator on each term on the right. So like here, we haven't written the numerator yet. We're talking about these. The numerator of each term on the right is a polynomial 1 degree less than the degree of the denominator. So here, think about it. What's the degree of this polynomial? Hopefully it makes sense that it is just 0. Or sorry, I take it back, 1, right? Because it's like x to the 1 power, x to the 1 power. So what do we do with that? Well, if it's just x to the 1 power, basically, we need to take a polynomial with 1 degree less than that. So what's 1 less than 1? 0. What's a 0th degree polynomial? We've already said it is a number or a constant. So you can think about that like, 5, 6, 8, whatever the number is, just some number up there. Now, this is kind of the issue. We don't know exactly what the number should be. That's why we have to write just a normal. We're just using capital A. Why are we using capital A? Basically because we ran out of constants, so we went back to the beginning of the alphabet, right? So this is like A is going to be some number. We don't know what it is, but we'll figure it out later. We're just trying to set it up properly. And to be clear, if this was like x squared, which can happen, you'd have to do ax plus b right here, right? So it's like mx plus b, like y equals mx plus b, a linear equation. Except we're just our unknown coefficients. We just go back to the beginning of the alphabet and grab new values. So hopefully that makes sense. But here, there's obviously not the 2 there. And then now, looking at this x minus 2, then what would we do with this? Basically, we would just have this, or I guess how should I word it? It would basically be the same thing, but we can't use A. I'll just say it like that. So here, this is the 1st degree, so we need a 0th degree. So I'll just write B. So B. So there you go. That's rule number 4. So we've done the 4 rules, and now our reward is that we've decomposed the fraction. So and this is a good time to talk about, by the way, what do we mean by decompose? Think about it like this. Think about you probably have heard the word decomposition before, or like decompose. Think about what it means. If you think about it, probably the context you've heard it in, even though this is a little gruesome, is a decomposing body, right? When like an animal dies, its body starts decomposing. That's obviously a term in chemistry or biology. What does that literally mean? What does it literally mean to decompose? Like when an animal dies? Basically, the molecules that made up the animal's body, like the complicated molecules while they were alive, start breaking down into simpler molecules, like gases, for example. That's why, like, again, not to sound gruesome, but like rotting bodies, like they like give off those kinds of like gases that smell bad. It's because like the molecules in their body are literally breaking apart. The word decompose literally means break apart. Now, obviously, we're in math, not chemistry or biology, so decompose means something different here. But it's the same idea. It's like in biology, decompose means you have one complicated molecule and it breaks apart into multiple simpler molecules. Well, here, just replace the word molecule with equation. You have one complicated equation that breaks apart into multiple simpler ones. And these, I'll tell you, once we figure out what A and B are, they're just numbers. These are going to be way easier to integrate, right? Like we can actually do this, and that's why we care about it as an integration technique. This we really can't integrate. Like the fact that we have this more complicated denominator causes problems for us. So that's the idea. So now that's how we set it up, and now we really just need to solve for A and B. Oops, we need to solve for A and B. How do we do that? Well, think about it. What would you do? Like, what we're trying to find which A and B could we make that adds up to, like, that makes the thing on the right equal to 4, or equal to the thing on the left, 4 over x plus 7 times x minus 2. Now, just by testing this out, obviously we can do this in kind of an unofficial way on Desmos with a calculator. So if we have, like, remember, what's the original one? I'll say 4. So 4 over x squared, 4 over x squared plus 5x minus 14 plus 5x minus 14. That, and then we have a over, what do we say, x plus 7 plus b over x minus 2. And then we just allow that. If you just start messing around with the values, like you can get, like, obviously if a gets bigger, that's kind of getting further away from what we want. There we go. That seemed kind of correct. So like that looks not bad, right? And then you can start messing around with the beat. Okay, so that's better. Just by like kind of experimentation. And again, it's like you can keep playing around with these a little bit. Like maybe this isn't perfect. It's hard to see exactly. But you can see that the answer is going to be somewhere around here, right? Like we're obviously a little bit off. So I'm not saying these are the actual answers, but these are the ones that make it work. Now, obviously, we can't use this technique like by hand, right? So that's using a graphing calculator, and also that would be very painful to do with your actual graphing calculator, right? That's only a Desmos is such a good tool that that's easy to do on Desmos. It's not easy to do outside of Desmos. So, what can we do instead? Basically, the way we do it by hand is we first get a common denominator, right? So how would we, obviously this is going to be the common denominator, the thing that we started with. So what could we do to get a common denominator on both of these sides? Hopefully it makes sense. Well, what's preventing this from being that multiplying by x minus 2? So let's just do that. X minus 2. So if we do x minus 2 divided by x minus 2, we would have that. And then over here, if we had x plus 7 divided by x plus 7, like that. And then if you combine these, so what do we have? We have a times x minus 2 like that. We get something like that. So basically, we know another way to think about it, obviously. So now the denominators line up. Now what we really need to do is we need to make the numerators be the same thing. So we need to make the numerators be the same thing. How do we do that? We basically just set them equal to one another. So 4 equals a times x minus 2 plus b times x plus 7. And then we need to find the a and b value that make these the same for all possible values of x, and that's the key. It can't just work for like one fluke of values. It has to work for all possible values. So what would do that? Like what values of a and b would make that happen? There's a couple ways to find this out. One thing you could do, I won't go through this. We'll probably talk about this next time, tomorrow. You could go through and set up a system of equations. That's the most painful way, honestly. That's the most complicated way. The simpler, less painful way is to basically strategically pick the x values that make it obvious. So that's actually your first step. So think about it like this. Let's start off with a. What x value could you plug into this equation to make it obvious what a is, what a equals? Think about it. Well, it would be whatever gets rid of b, because as long as a and b are both here, we're going to have two equations, one equation, two unknowns. We won't be able to solve that in its current format. But if we could somehow get rid of the b, well, then we would just have a, and that would be obvious. So, because really what we're taking advantage of the fact that the thing on the right has to be true for all possible values of x, which means we have the freedom to try whichever one we want and test that it's true for that. So let's just try this. Let's just try x equals -7. Why do I say that? Because if I plug in x equals -7, this thing's going to equal 0, and b is going to go away. So if you just plug in x equals -7 and then see what you get, what do we get? A -7 minus 2 plus b -7 plus 7. -7 plus 7 is 0. The whole thing is 0. So you get 4 equals, and think about this, -7 minus 2, that's -9. That times a is -9a. And then you can solve it. A equals -4/9. So a equals -4/9. So there you go. Now we know that a has to be -4/9 because it's the only thing that could make sense when x happens to be -7, which we intentionally chose to make it obvious, right? And you can do basically the same thing the other way, right? What would make it obvious what b was? Well, if we got rid of a. So what could we plug in to get rid of a? +2. So let's try that. So if I plug in x equals +2, so x equals +2, what happens now? So basically, like wherever we see x, we're now going to replace that with +2, right? So right here and right here, it's going to be 2 and 2. And then think about what happens. 2 minus 2 is 0. Now a goes away. And then what are we left with? We're left with 4 equals b times 2 plus 7, 9b. And now that's easy to solve. B equals +4/9. So there you go. That's how we find the a and b that make the decomposition true. And now, again, let's test it on Desmos. What are we? So the answer is -4/9, or if you think about the decimal, -0.4444, just repeating forever. And this is just +0.44444, repeating forever. That's why we're so close, right? If I do 4/9 here, if I do -4/9, and then I make this +4/9, you see how those are both close to like 0.5. Now it works. It's literally on top of the curve. It's that is they are the same curve, I guess is the point. Those a and b values work. So what does that all mean? That all means that if we go back to our original decomposition up here, or whoops, we go up to the original decomposition that we set up. If I pull this down, the original decomposition we set up, if we look at this, basically what we just determined is that a is equal to -4/9. So as long as a is -4/9, and then b is +4/9, this thing is true for all values of x. The function on the right equals the function on the left. There you go. We just did partial fraction decomposition, but we kind of have been ignoring the calculus part this entire time. Remember, the whole goal of this problem was to find the integral of the thing on the left. Right? That was our whole original goal. So if we're going to do that, basically you can just integrate both sides. That's the trick. The trick is you don't even integrate the thing you started with. You integrate the decomposition, like the sum of simpler functions, if you will. Because it's a lot easier to do that, right? Like, because basically the sum rule for integrals exists. If you're going to integrate the sum of this thing plus that thing, what you could just do instead is just integrate the sum of each thing individually. So it'd be -4/9 integral 1 over x plus 7 dx, and then plus +4/9 or plus +4/9 integral 1 over x minus 2. What would that be? Well, what's the integral of 1 over x plus 7? And this is where you have to be comfortable with your integral rules. And you kind of have to be able to do a little bit of u sub in your head here. This is not a hard u sub, but think about it. It would be natural log of x plus 7. It's basically the way you do the simple u subs in your head, or actually, let me back up. The way you do a normal chain rule, u sub is really the opposite of the chain rule. Chain rules are basically take the derivative of the outer function, leave the inner function, multiply by the derivative of the inner function. That's the rule. So I'll write that again. So like the normal chain rule, and I've covered this elsewhere, I know, but chain rule is multiply by or derivative of the outer function. So derivative of outer function, keep the inner function the same, multiply by derivative of inner function. What we're going to do here is essentially the opposite of that, the opposite of those rules. So U sub, or which is the opposite of the chain rule, so anti-chain rule is what I like to call it, because that fits the pattern better. You do what's the opposite of taking the derivative of the outer function? The antiderivative of the outer function. Keep the inner function. There basically keep means no change. So okay, there's nothing to do the opposite of. Hopefully that kind of makes sense. Multiply by derivative of inner function, divide by. So I'm just literally doing the opposite rules here of the normal chain rule. So think about it. What's the outer function here? 1 over x. What's the inner function? X plus 7. What's the antiderivative of the outer function? 1 over x? Natural log. So natural log of something, and then keep the inner function, x plus 7, and then derivative or divide by the derivative of the inner. The derivative of the inner is 1, so you just divide by 1, but that doesn't do anything. So hopefully that makes sense, but you really want to get to the point, like when you end up with just what are called linear denominators, it's actually very easy. It's always like something natural log, right? You can just pull the constant out, natural log. That's basically the answer. Sometimes it gets more complicated. Like I said, if you had like a 2 here, you'd have to divide it by 2, like to do this last step. But as long as it's like 1, that's pretty easy. It's just like literally natural log of that thing. And this one will be plus 4/9 natural log of x minus 2. And then because this is an indefinite integral, you also have to remember plus c. But there you go. Hopefully that process makes sense. That's like a simple walkthrough. Again, it's not a simple technique, but this is about as simple as it gets. It only gets harder from here, unfortunately. But that's how you do it. That's how you take the logarithm of, or sorry, not take the logarithm. That's how you take the antiderivative of complicated rational functions. You basically decompose it instead of having to deal with one complicated function that's hard to deal with, because this is the thing, we don't really have like we don't have like anti quotient rule. That's kind of the problem with this. So that's why you really I would rather deal with 10 simple ones than one complicated one. Honestly, I'd rather deal with an infinite number of simple ones, because as long as they're simple, they're like one line of work and it's pretty easy to do. This thing's actually very hard to integrate by itself, which is why we don't even really try to do it. We try to avoid that with this technique. So there you go. Hopefully that makes sense. So that's partial fraction decomposition. It does get more complicated than this, and like over the next couple of days, we'll talk through some of the more complicated methods. But that's how you do it here, and then hopefully that makes sense. If you have any questions, as usual, feel free to just drop them in the Skool community. Otherwise, we'll continue working through. All right, hope that helps. Everybody have a good day, and I will catch you later.